Welcome to the another session in Frontiers in CFD. Numerical analysis of airflow cooling in a cylindrical lithium-ion battery module with Baffles arrangement. So the today's objective is to develop an accurate 3D model of the cylindrical lithium-ion battery module with Baffles to ensure realistic airflow and thermal analysis. Second objective is to create high quality mesh, apply boundary conditions, define material properties, and the configure solver settings in ANSYS Fluent for accurate flow and thermal analysis. Third objective is to run the setup, generate the temperature contours and temperature streamline using ANSYS post-processor tools. So this is the geometry that we are going to prepare today. So it has cells, then we have the fluid zone, and surrounding to the cell we have casing, and to the casing the fins are been installed. So the geometry preparation will start with the design modeler. So these are the simulations that we are going to visualize today. So with respect to the flow time, so you can see the air which is taking away the heat from the cell. So you might see some variations in the terms of cell temperature, which has been here as comparatively darker side on the other side. So we are running it for around 1200 seconds. So this is the first setup animation which we are run. Second setup animation relates to the cell temperature. So how the cell temperature varies with respect to flow time, so that we are going to visualize. So this is also done up to 1200 seconds. So with the help of this, we'll see how this can be done in detail, right from preparation of geometry to running the simulation, how to plot the chart. So this is all going to visualize in this particular session. So today's design is actually inspired by one of the configuration which you are able to see here. So let's proceed with the workbench. Start with the fluid flow fluent option. Click on new design modular geometry. First of all, set the units. So let's create a primitive that is a box. So the dimension which we are going to take is 136 along x direction. Z component is along 136. So y component will take it 70. Okay, so let's make it add to frozen and then generate. So this is the geometry which has been prepared. So next is on ZX plane. I will go on to generate sketch. So just visualize the ZX plane now. So first of all, now again we need to follow the sketching operation which is to be done. So first of all, draw a circle. Let us say this is diameter of that, we will specify it is 32 as for the dimensions. Distance of this from one end we will specify this one. Similarly, distance from the center with respect to this we need to specify. Okay, so the thing is the total dimensions are 136 here, and this is also 136, out of which the fins of length 126. So I will give 5 distance in addition to this. So 16 will be diameter here. 16 will be radius here, as 32 is diameter. So 16. Then 126 is your the fins dimension which is present here. So accordingly we are going to specify the distance. So this will be equal to, so I took 31 here. This one I will take 31 on this side. So let's make it generate the first sketch. Now I need the distance between this and the second one. So take the dimension, put a line here. So the distance between these two, so 16 is your radius. So 16 plus 16, that is equal to 32. 32 plus we need a distance which is equal to 10. So I will take it 42 here. One more time, draw a circle of same radius. Then one more time, draw a line from this point again here. Dimensions again, I will take it 42 on this side. So one more time, draw a circle. Okay, so let's modify the dimension. So V2, so I just took it 26. Okay, now looks to be correct on this side. Similarly, I will take it H3 also. Let's say 26 and we'll accommodate it. Okay, now this is done. So I need more of such, let's say here. So now carefully take the dimension, that is equal to 42 here. Similarly, one more line you have to draw of a distance of 42 from this. So let's take this is equal to 42. So now repeat the thing which we have generated. Hit this and this. So click on end set first handle and click it here. Okay, so the sketch has been generated. Click on end. Now you have to do the slice operation. So I just click on slice. Not slice operation. So just go to the extrude operation, make it apply and select slice material with the help of sketch. So this foot I 70 and just click on generate. So you can see now the cells are being generated here. So this is how the diameter which you have taken 32 and height of the cell is taken as 70. Now we need to generate a fin portion for this particular arrangement. So that fin portion along with the casing. So I will just provide one more sketch here. So click on sketch. Now this is sketch 2. Go to the sketching. So one more time I just select a circle. I will draw a circle here. So dimensions of this, now 32 is your diameter. So I will select this is equal to 33. So that will act as a casing. You can either take it 34 also if it is visible as a casing. So this is material as a casing. So 1 mm is the thickness which we are considering here. So let's make it generate. I need to copy this. So I just click on this, click on copy, set end paste handle. So generate wherever it is required. So this is all about casing which we are doing. We provided a thickness around 1 mm. You can provide different also. Click on end. One more time click on extrude. Instead of add metal, make it slice metal and generate. Now you will see the casing part is also visible here. So this will be your casing part. This is your fluid zone along with this fins which you have to generate.
Now the thing is, I need to generate fins of 1 mm thickness. So we are trying to have fins which are connected here. So for this I will do one more thing. As for the fins, dimensions are slightly on the different size, so I will click on create, say primitive, say as a box. Instead of add material, I will make it slice material. X component I will take 126, Z component also I take 126 here. So I am taking X and Z component as 126. Now I need to shift this by distance that is equal to 5. X coordinate I will shift it by Z coordinate also 5. So now this will represent my the fin zones. So this is how you can see the geometry as of now. So now one by one we need to create the fins for this particular arrangement. So for this case I need to slice the geometries along ZX. So we'll do the slicing. For this I need to create planes. First of all, create plane. From ZX I just put it offset Z. Now total height available with us is 70. So based upon this 70 we need to prepare the casing. We need to prepare the fins for this particular arrangement. Thickness of the fins are 1 mm. So depending on how many number of fins you want, accordingly you can change this particular dimensions. So we are going to generate total 5 fins. Accordingly we will proceed. So first of all I will take a dimension that is equal to say 2.5 from this. .5 plus so total is 14.5. I am taking the first. Make it slice. So this is the first. Create one more plane at a distance of offset Z by equal to 1 mm thickness. Generate. Do the slice operation. Make it generate. So one more. From plane 5 I will take it now offset by a distance that is equal to 12. So make it generate. Do the slice operation. So one more thickness I require that is equal to 1 mm. Offset Z 1 mm thickness. Make it generate. One more time. Offset Z. Now distance is equal to 12. So let's put it 12. Do the slice operation. One more I required. So make it offset Z by 1 mm. So let's make it generate. So do the slice operation. Okay, I think one slice operation is left for plane 7. So do slice operation for plane 7. Make it apply. Generate. So we are at plane 9. One more plane I have to generate. Say offset Z that is equal to 12. Let's make it generate. Do the slice operation. Make it apply. Generate. So one more I will require. Make it offset Z by equal to 1 mm. So you can provide the thickness as for your requirement. I'm just trying to do this with the help of 1 mm thickness. Okay, so in this way the fins are actually been produced. Now we need to do some rework for the geometry. So accordingly we'll proceed. So first of all, the outer parts are same, so we'll try to make them as the same. Ensure that you have selected all of them. So create boolean, make them unite. So this is your outer part. Now next is I just hide this body. So now we need to define the casing along with the fins. So we are assuming the casing and fin to be made up of aluminum as a material, which is for your cell. So one by one we'll define the materials now. We'll unite the geometry for your cell and then we'll proceed. So this is your fluid zone. In between fluid zone, this is fluid. Lastly is your fluid zone. So form new part. I will say this is your fluid. So you can turn this definition to fluid. So this is for your fluid. So now I will hide this part. Okay. First fin, second fin, third fin, and this is your fourth fin. So if you are considering the fins and casing is of same metal, you can select this outer part, this one. So this way you have to do it for all layers. Assuming that you are considering the fins and casings are of same material, so in that case we have to do this arrangement. So let's visualize it from this side. Okay, so let's create and make the boolean operation, make it unite, generate. So what we have now, this is the fluid zone. Okay, so this operation is not completed, so one more time. Let's click on, okay, so just delete this. So let's select all outer region first. Or you can form new part and then you can make them as a unit. So this is this. Only outer region I have selected, so make it form new part. So I will specify this is fin casing. Say fins and casing. Okay, so let's hide this body. Now we'll be left with only cell portions. So I select it all. No, select will all not work out here. So this is the cell which I am having. Okay, so along with the casing cell, we have some casing also visible here. So we'll have to make this unite with respect to the earlier geometry. Okay, so we'll do is select this body, this one, this one, the one which is outer. So you have to do it for all layers. This one. So this is actually the casing part. So that you are selecting. This is already selected. All four. So just check the count once. So 4 4. You need to select all, then only. Okay, so I will form a new part for this. Okay, so I will hide the part 3 now. So fins and casing here, this is your fluid. So we hide the part now. Now this is left with only cell. So select all. So create a boolean operation, make it apply. So this is your cell part. So this is casing part. So I will just unite these two. So go to the boolean, make it apply. Earlier we are seeing the boolean operation was not successful because it was showing yellow highlight. Now I have specified, you can see the green highlight is there, so it means things are correct for us. So this is fluid zone, this is your solid, is actually fins and casing, so I can define this as fins and casing. Okay, so this is the again fluid zone. So this is cells, so one by one we'll just try to sort out the cells. Okay, so I will make it form new part. So let's define this as cell. This is your cell. So define all of them as cell. So give the same name so that later on we don't need to worry about the putting the boundary conditions here. So let's put it cell. So have it here. Make it cell. Last one is also cell. So now this is a fluid zone which we are having. So we'll define this also as a fluid. So make it copy, put it everywhere as a fluid. You can give the respective name also of the fluid which you are using. So this is your fins and casing. Then this is your fluid. These are all your fluids. Then this is your cells. So the geometry preparation is done. Now let's check this. Okay, this is also your fluid zone. So I will just combine this fluid and this. So this is also, I will specify this is a fluid. Now I'll combine the two fluid zones. So make it fluid now. So this fluid and this fluid I will go on to make it combine. So make it boolean and make it apply. So this is your fluid zone along with the casing. So likewise now the geometry has been prepared. So still I will make it show all bodies. So the outer region is fluid zone, and between that we have the casings provided here. So likewise the arrangements are with us in front of now. So thickness 1 mm has been considered. Now with this thickness of 1 mm, now we'll proceed for the simulation. So ensure that this is a fluid, and in the definitions also it is fluid. So fins and casing, this should be solid. So cells there should be solid. Once the geometry has been done, we can actually proceed for the next part. So let's proceed with saving the work first. So create a new, select on folder. So total 9 cells with fin and fluid. 9 cell with fins and fluid. So this is the folder which I have prepared. Just click on the copy address, make it save, and now let's proceed for the mesh part. So click on edit. So let's open the mesh. So fit to zoom. Let's generate an arbitrary mesh first. Okay, so this let's see the statistics. So very limited number of nodes and element as of now. So I just put it 0.005, and let's check the mesh. So considering 1 mm of thickness of the fin, we need to generate the mesh so that the elements on the fin size of 1 mm thickness will also on the proper side. So let's go with 0.001. Earlier we took 0.005. So depending on the size of the mesh which you are selecting, depending on your element size, the time requirement will be more or less. We are slightly going for on the finer side. The same integration we can do with the PCM also. So whatever the surrounding material which we are having, so we can define as a PCM, and accordingly we can try to do the simulation also. So that will be integrated with the fin and PCM. Okay, so let's go with the given size of the mesh. Once we'll just check out the fins portion, mesh at the fins portion, and then we'll just proceed. So this is for your fins portion, so looks to be better. You can go slightly on the finer size as well. So I go with the same size, make it show all bodies. So first of all, go to the cell. I will hide all other bodies. Then I will select all the faces of the cell. So this is the first, second, third, fourth, fifth, sixth, 7, 8, 9. I will define as cell boundary. So make it show all bodies. So this is your actually casing boundary. You can actually define it. I just put it cell boundary. Then I specify this one corresponds to as a inlet. So specify this is inlet and specify this as your outlet. So depending on which direction you are considering, so accordingly you can define inlet outlet. So which are the where the places which are important things for me. This is your inlet, then we have outlet, and this is cell boundary. So once you are satisfied with this given size of mesh, just click on update. You will see the mesh translation to fluent successful options. Once this option is been visible, you can actually proceed for the next step, that is for your setup. Okay, so you can see the mesh translation to fluent successful. Just click on save button and now you can proceed with the remaining. Okay, the workbench window, this has been saved. So before proceeding for the setup, we must have some properties of the material, that is density, specific heat, and so if you are satisfied with the given mesh, you can proceed for the next step. So I just close the meshing part, which is we don't require further. So click on edit, specify the number of processes your computer can run. So I just put it around 16. Let's click on start button. Now you must be handy with the properties, density, specific heat, and thermal conductivity for the cell, along with what material you are using, whether you are using air as a working fluid or whether you are using some other working fluid. So you need the properties of that. Along with that, if you are going with the PCM, you must have the properties of the PCM as well. So here we are considering the combination with air as a working fluid. So accordingly, we'll proceed with the setup part. So once this is completed, you will see arrows along with the model which is visible here. So select the transient. Then I put the gravity, that is minus 9.81. The gravity is in negative direction over here. So just go to the model. I just click on energy equation, turn the energy equation on. Then viscous, I will select K epsilon model, enhance wall treatment, thermal effect, curvature correction. So let's make it okay. So we are not using the solidification melting model. We are using the PCM as a fluid as a material over there. So you can select that. Next, I will go with the material. So here I will by default consider solid aluminum is there. So that is again we require to keep. So I just put it lithium here. Lithium cell. I again write the same name, lithium cell. So I will put the properties with respect to my one of the reference I have taken. So it is 2320. Density specific heat I will put it 900. Thermal conductivity I will put it around 0.83. Let's create here. Next thing which I am doing is go to the Fluent database. One more time, just select the aluminum, make it copy and then close. So air is a working fluid, then aluminum for your casing, then lithium cell which I am considering. So these are the material we are proceeding with. So zone types, let's say fluid. By default the option is here because we haven't added any other material, so you don't need to go and change. So just click on edit. Lithium cell, select source term. So just put the heat generation number of energy sources. I will put some constant value, that is around 2242
000 watt per meter cube. Let's make it OK. Let's click on apply and let's click on close. Fins and casing, the material should be aluminum. So select the aluminum material and then proceed. So let's close this. Now boundary conditions, put some value of velocity at inlet. So the inlet velocity that we are going to specify, let us say around 0.5 meter per second. Make it apply. You can change the parameters with the different values of velocity. So just go inside of cell boundary contact region. By default the material is lithium cell, so I will keep it as it is, will not make any changes for all the cell boundary contact regions. Okay, so this is your wall cell, just go inside. So wall cell is lithium cell, wall fins and casing, just go inside and select the lead aluminum as a material, then click on apply and then click on close. Now next thing is which we are going to report definition. So okay, so first we'll do is the initialization we'll do and then we'll specify the report definition. So just to check which are the parts which have been available. So first of all, click on initialize, then we'll go on to have the report definition over there. So once it is initialized, we'll set the animation first, and once we are setting the animation we can proceed for the solution report definitions. So select contours. So here I will select temperature, I will select the total temperature here, I select all, go to the color map option, instead of exponential click on float, make it apply, then close, click on save display. Now your the entire object will be displayed once it is loaded. So this is we are doing to see the object properly. So I will say total temperature system, that is animation 1. Let's make it OK. Then one more time just click on this. Here I will select total temperature again, but it will be for only cell. So cell boundary contact region I am selecting here. Okay, just go to the color map option, float, make it apply and then close, click on save display. Now you will be visible with only cells. Now we need to select the regions for them. So I just select here. So definitely this is not the region which we are, this is fins we are appeared. Okay, so let's see one by one. Okay, so we need to properly select the contact region in order to visualize the cell cover part. So just say 2 is not there, 3 is also not there. Sorry, wall cell. Okay, now you will see it is entire complete portion is there. So this is when we are in the animation we are able to visualize the things. So this becomes slightly easy. So even if you want to just check the fins, just like in earlier case we have selected the contact regions here, so the fins was visible, so you can actually select the respective fins and you can visualize the temperature at that fins also. So wall cell and cell boundary contact region we have selected, so make it apply, then close, so click on apply, then close. Now go to the contour, I will say cell temperature animation. Now it becomes easy for me, and go to the report definition. So just go here. So here surface report is there, then volume report is been also available. Surface report I will go with the area weighted average. So select temperature, I will select the total temperature here,
then go to the print console. So I just put it total temperature, I put it system report definition. So just make it OK. Next, surface report area weighted average. I will select temperature now. So select total temperature. Now I will select cell boundary contact regions here. So lastly you have to go for the cell last. So now this becomes easy for us because we already done this, visualize this in while setting the animation. So now it becomes easy for us to select. So cell temperature report definition. One more thing which is important is that we have defined this cell boundary in the mesh, so that's why it is visible. Otherwise it could have been very difficult to identify, just like we have to check it each and every src or trg, then accordingly the selection could have to been done. So this become easy if you are defining the things in mesh what we have done. So let's click on OK. Now click on close. So now we'll start with the calculation activities. So let's put it around 10. So in calculation activities I will make it auto save, let us say after 20. Then go to the run calculation. Apart from this, if you want to visualize the inlet and outlet temperature, so that you can also specify in report definition here. So I will just proceed the calculation for this arrangement now. We are done. I just initially provided less number of times, that is only 10. Accordingly we'll proceed. So let's click on calculate. Now we took air and we have specified the velocity of air. With that particular velocity now the calculations will proceed. So depending on the mesh requirement, the things may take some time. So whatever the report definition, whatever the animation which we have set, now this report definition and animation which we have set will be visible once we have performed the first 20 iterations. Then all these windows will be visible in the here. As I said, you can set PCM also. So while you are setting the PCM, you need to specify the solidification and melting option also. So the iteration process is on its way. Till the time first 20 are not completed, you will not see this appear in the window. So we have to wait first for the first 20, then whatever report definition we have set or whatever animation we have set, this will be all visible in the this particular window which is available. So definitely we might have to run this for a long time in order to visualize the complete results. So depending on the simulation, depending on the mesh size which you have selected, the time for the simulation will be more or less. So if you are going on the slightly on the coarser side, the time requirement will be less. If you are going on the finer size, then the time required will be more. I have just tried to use the default mesh, not necessarily always you can go with the default kind of mesh. You can have the element sizing on the respective element wherever it is required. Just for to reduce the complexity and to reduce the time required, I have selected a particular element size, and with that element size I tried to do the simulation. So a respective element sizing on cells, respective element sizing on fins can also be done.
So we are almost on the completion of the first 20 time steps. Now one by one all the windows will be visible to us. So you can see here. So the first case which we are observing here, the cell, this is cell temperatures. This is again the fluid which has been flowing. You can see the cell temperature curve which is specified here. Then this will represent the total temperature of the system curve. So we definitely require to run it longer time in order to visualize it in more better way. So as of now you can see how the fluid is taking heat. So that has been visible. So cell part as of now on the height, we can say slightly on the higher side of the temperature. You can see this contour. So if you use different working fluids, so accordingly the parameters may also change. So if you just want to see this the temperatures on the fin, so that could have also been set as an animation. So in that case you must aware of the fin portions and select it. So we are still running the simulation. So we are around 7 time steps. You can see the curve here. So we have to run it further in order to visualize it in more better way. So we are around 95 time steps. So we can visualize the contours of cell temperatures. Then this is the contours of total temperature of the system. So here, and we can see the cell temperature report definition value. Then we have the total temperature system. So right now we are on around 98 time steps now. So we'll have to wait for some time in order to visualize it more better way. So this is how the simulation which has been carried out. So we'll run it further to see how the effect, how the temperature will change with respect to the flow time. So we are around 1042 time steps, that is the flow time. So for this flow time we are observing the temperatures are around say 331.99. So this is for total temperature of system. So you will see cell temperatures will be slightly on the higher side, that is around 339 which you are observing right now. So this is how the temperature variations for the cell which we can see. So this is with air as a working fluid. So let's check wait for this curve to get flat. So we have almost completed around 1200 time steps as well as the flow time. So the curve is likely to become flat, you can see here. So the tendency of the curve has become flat now. So this is the contours of total temperature of the cell. This you can observe the contours of total temperature of the system. This is your cell temperature report. So you can see the curve right now. Total temperature of system. So this is again will show you the temperature. Then scale residual, you can just proceed here. So the calculation has now completed. So you'll see once you'll see message, then you have to click on OK. Okay, so this is what we are done for the cells which we have. Okay, so let's save the image file for this. So how to save the image file for this? So we'll just try to do this. First of all, save the work, then we'll save the images file. So once the saving is done, okay, so you can see the option here. You can see the save picture option available. Then you can set the resolution. Let us say I set it to 4K. Click on save button and simply go to the folder. Okay, so here what I will say, I will create a new folder, putting the name as images 9 cell with fin. So go inside and click on OK. So one more time, just start it from again. So click on save, go to the same folder. So what is this image? This is image is the total temperature system. This is actually the animation image. So just click on save, close this. Then this shows you the contours of total temperature cell. Cell. So I will put it as animation image. Close this. Then this is your cell temperature curve. So simply go here, just put it cell temperature curve. Close this one more time. So here you will see the total temperature system. I'll put it as curve. Close this window. This is your scale residual. So just go. Okay, so save as here. Okay, so this is what we have saved the images. I just go to the folder to visualize the image. So simply go inside. So this is where we are working. So images. So let's see the large icon. This is your cell temperature curve. This is your scale residual. This is total temperature cell. This is total temperature of system, and this is your total temperature system curve. So in this way we have generated the curves. Now I will go inside. Let's say here, go to DP0, click on triple F, go to the fluent, view as a large icons. Now search for report definition file. So you will see we have set the report definition earlier here. Cell temperature report definitions 1, cell total temperature is to report definition. So we have to search in this particular box, in this folder. So simply take it downward. Okay, so you will see here you have to search for the file here. Okay, so you'll see the cell temperature report definition out. So this is one of the file we are having. We have to search the second file also. So let's come down. Okay, this is your second file. So simply copy this file here, go inside, again go to the same folder where we have saved the images, just paste the file. Now let us say if I open this first file, cell temperature report definition, I just click on notepad file, you will see all the temperature values which are available here. So that will show me cell temperature values with respect to your flow time. So you can see the temperature has becoming slightly on constant side. So this is the total temperature system. Now next one is, again I have opened the total temperature system, earlier was cell temperature. So this will represent me soil temperature values. Okay, so these are the two curves we are having. So if I want to generate the curve, for this we can make use of ChatGPT as well. So let's what you have to do. I just put it here in ChatGPT. So I will ask it to plot graph between cell temperature and flow time. So once this file uploading is completed, we will ask it to please plot chart of cell temperature versus flow time. Now you will see it will take some time to analysis, and you will have of cell temperature versus flow time as a graph that will be generated. Okay, so you can see this is the graph which has been generated. You can save the file as well, like if you want. Okay, so let's save it in the same folder which where we are working. So let's go inside. So images file, I will put it as cell temperature versus flow time. So this is we are done with ChatGPT. So I will save it. Now one more thing which we are having, I have this total temperature versus flow time. So simply take it here, put it into ChatGPT, then ask please plot total temperatures of system with respect to flow time. Once it is done, so again it will produce one more good chart which we have seen earlier. So the notepad file we are using, with this notepad file we can directly put this file to ChatGPT, and it will generate a kind of we can say the curve which has been generated like this. So you can save the file as well. Let's ask one more time. Okay, so yeah, I think okay, so likewise the first one is done, you can do it for the second also. So this is what we can do with the help of ChatGPT. Another thing, if you want to do it with the help of Excel, I just show you how it can be done with Excel. So I just put it charts here. So go inside. Now this is I will first go to the first notepad file. Let us say I will go with the total temperature system. Then just copy these values from first to the end point, whichever you are having. So make it copy. Then go to your Excel file. Simply Control V. So here I just have text import wizard. So I just click on new, next, sorry. Click on next and let's click on finish. Now you will see three different things which are available with us. One will show the flow time and time steps. This is the flow time and time steps. So as we have time step size and flow time as a, if you see the time step size is 1, and that's why time step and flow time will be the same. So we actually don't need a third column here, so I can just delete this. So let's define this as say total temperature system. So we have took the values here. Now let's see how to plot charts for this. So select all the values which are available with us. So just go to the recommended charts. You can see the option which is available first. and this is how you can get the temperature versus the flow time. So you can give the labels to this axis titles. So here I can put as flow time, and here I can put as temperature. So this is total temperature of the system, so I will just put it as total temperature, and this is your system. Okay, so total temperature of system, this is the curve which we have generated on the left hand side. This is your flow time. So in this way we can generate charts. You can change the design of the charts also, whichever you want as per the requirements. So some modification can also be done. So likewise the charts can be prepared as you can see here. So this shows you the total temperature versus flow time. Now similar on the similar note, I will just show you how the charts that can be prepared for this is the first chart which is related to flow time and system temperature. Okay, so now let's see cell temperature, how it can be plotted. So I will put it cell temperature versus flow time. So let's go back to the close this notepad file for total temperature system. I will just go back to the notepad file of cell temperature versus flow time. So let's put it open with notepad file. Okay, so not visible, just a minute. Okay, so this is one. So let's select it from 0, select all the values. Okay, just go to the Excel file, paste your values, so Control V. So here I will use text import wizard. So click on next, click on next, click on finish. So I may not need the third column, so I just delete it. So I will just go with the 2 here. So here I will put it as flow time. This is your cell temperature. Okay, sorry. Okay, so simply select this two and go for here inserts. So go to the recommended charts, you will select the option here. So now you can see the cell temperature versus the flow time. If you want, you can put some labels over here, axis titles. See here, I will specify this as your flow time, and on this side this will be your cell temperature. Okay, so likewise here you can specify cell temperature versus flow time. This is the title, and likewise if you want some different design, you can select the design as well. So there are many designs available, out of which you can go with the one which has been required. So this is how the chart has been prepared. You can simply use this chart for your analysis point of view. So that's it, how it can be charts that can be generated with the help of Excel, how the charts that can be generated with the help of we can say ChatGPT if you are having, so that can also be utilized. So now we have seen how to generate charts with Microsoft Excel and ChatGPT from your ANSYS file. So now let's uh, if you want to save the animation, you can just go to the playback here, and you can select the animation frame. Instead of animation frame, we can select the video file, and accordingly you can we can save the animation which has been specified here. So if you want, you can actually play the animation as well here. So right now this is the first stage which has been showing. So if you want, you can save the animation files as a video file. So you can see the option which is available as a video file. Video options is there. So you can select the number of frames which is required. Let us say I put it 60. Instead of original resolution, I can set it to 4K. And here also again I can specify best quality and make it OK, and click on OK. So once you click on write, this files will be saved. Where these files will be saved? These files will be saved in, again, sorry, we'll go back. Okay, these files will be saved inside here. So you have to go to dp0 triple f save fluent. So inside this the files will be saved. So when you write it, it may take some time depending on the system configuration. So this is the way of we can say writing the files. Next is your, if you want to generate the reports, how it can be generated. Simply click on report outline here. Once you click on generate, this export option will be visible to you once all the process has been completed. After that you can see an option of export to PDF. So a kind of PDF file will be generated which will show you all the boundary conditions which are available, what boundary conditions you are specified, along with the animation images will also be visible along with the charts. But one thing is the animation images will be available till the current running time. If you close the app and then again try to visualize the PDF, in that case it may not be with animation window. Otherwise the graphs will be there and the boundary condition we are specified, they will be as it is. Okay, so last part which is related to result. So just go to the edit. Now when you go to the edit, so now we'll see how to generate a simulation video of this with temperature streamline or the volume rendering which we are having, so that we are going to visualize it now. So first of all, a blank window will appear when you first time open it, the result part. So this may take time depending on the system configuration which we are having. So always try to ensure that there is sufficient space available with your computer. So first of all, I will just go to the volume rendering here. So instead of pressure, I will select temperature. Instead of global, I will put local. So depending on the resolution your computer can handle, you can put that value. Let us say I put it around 150. So I set it to local. You can specify as per your requirement also. Like if you want the volume rendering to be within specific temperature limits, so accordingly you can specify the temperature limits as well. So again, it may take some time depending on your system configuration. Once it is loaded, you will see all the temperature contours available on the computational domain. So this is the result part of that is the post processor part which we are having. So you definitely need a better configuration to run this volume rendering, as well as you can save the video files with the same. Okay, let's wait till the object is loaded. So you can see the progress here is 0%. If you are finding it the system is not responding, you have one stop option available. If the system get hang, so that time you can use that particular option. So let's wait once this is completed. So you can set a little less resolution also. Higher the resolution, the time requirement will also be more. Okay, so let's wait. Now you can see the file has been loaded here. So let's go to the volume rendering here. This is the option which is available. Now let's click on left center, go to the appearances, put it fixed. Number of value tricks I will put it 11. So size, let's put it to 1. Let's reduce this size, and now let's click on apply. So you will see a proper temperature scale which has been visible here right now. So we are visualizing the volume rendering as of now. So you can change the view of your object depending on the requirement. So you can see the animation. So this is starting point and this is your ending point which is available. So now I just shall show you the second thing which is related to streamline. So just click on streamline, just click on here, start from, let us say, inlet. Let's put some points. Let us say I put it around 300 points. So now let's put the variable here. So I will use the variable in terms of velocity. I will put temperature and put it local, and let's click on the apply button. Now once you click on apply button, you will see some temperature streamline as well. So you can just change the number of temperature streamlines, which are points which are available. Let's say it's around 500 I put now. Okay, so let's go back to here, and instead of time step animation, I select sweep animation, and let's see how to visualize this. So you can see the particles which are coming. These particles are taking heat from the cell and they are moving ahead. So while taking the heat from the cell, you will see some changes in the color contour for the particles. So this changes in color contour will indicates the temperature taken by the cell or the heat taken by the cell, sorry, the particles from the cell, and that's why you see some changes in the color combinations for this. Okay, so let's click on pause button. So this is how we can visualize the temperature streamline, so particles can also be visualized. Now if you want, you can save the movie as well. So just go to the here, you can select the resolution 3840 and let's say 2160. So if I go with advanced, you can save as image file, then you can select the frame rate, let us say around 60, and you can select the output directory file as well. So just click on, let us say, a folder, prepare a folder, let us say 9 cell with fins and casing, and let us say the fluid flowing. Okay, so this is the one folder which I have prepared here. So just click on OK. When you click on save movie, just go and select the same folder which we have generated, 9 cell casing, and let's click on save button. Once this is done, you just have to click on play button. So once you click on play button, the image files will be generated in that particular folder, and accordingly we can visualize the things. So how to do this? Let's click on play, and let's go to the document folder here. So this process may take some time. I will just go with 9 cell with fins and casing. So right now it is showing the empty folder. So let's wait for this process to complete. So this here, one by one the image files will be getting generated. So let's open the folder again. Now you can see the image files are getting generated. So this is how the image files are we are able to generate over here. So this is how n number of files are generated. So this will take some long time, as I said earlier. Till the time you don't have complete the 1000 frames, this process will not get completed. So this is, again, as I said, is a long task to go with. Okay, so let's wait for the process to occur, and accordingly we can visualize this, we can say, result. So once these frames are completed up to 1000, at the end of that you will see one video file which has been generated, just like for this case we have seen the fluid is flowing from inlet to outlet. So the entire video file will be generated, and this will be at the end of 1000 we can say images which are available. So this is way how we can say the simulation can be done. Then we have seen the how to prepare charts with the help of ChatGPT, or we can do with the help of Microsoft Excel file. And lastly, when we are in the result, how to prepare the video files, how to prepare the animation images, so that we have seen. So after generating the report, you can see export option is visible now. You can click on export as a PDF. Go to this file. So click on OK. So now in this PDF file, you will be able to, okay, in this file now you will be able to visualize all the boundary conditions that have been applied, as well as uh, the details of mesh. So the one which is visible right now, it will give you all information, that is mesh quality, mesh orthogonal quality, then physics model, material properties which you have set, so that will be visible here. Then cell zone condition, boundary condition which you applied, they will also be visible. Reference values will also be visible. And lastly, now this is the graph which is represents scale residual will be visible. Then the total system temperature graph will also be visible here, and the cell temperature report definition. So this is the various parameters that are going to be visible. So you can plot, you can save this file as a PNG also. Here also you can save the file and you can visualize it. Okay, so this is a part related to the we can say the graphs. Next thing is which you can observe is the contours once and contour two, whichever they are visible, and you can actually play the animation here also. So you can just click on play animation and you can visualize the animation as well. So you can save the file as well, and you can observe the total system temperature animation in the second window also. But when you save the PDF, that in that PDF all this uh, just a minute. So this is the PDF which has been saved. So in that PDF you will be able to see the graphs, but the contours images may not be able to play. So this is what we can visualize in the. Okay, so next step, as when to visualize, as I said earlier, the animation videos which are been saved, where to visualize the animation videos. So that I will show you. Just go inside DP0 triple F, then Fluent. So this is the first image which you are observing. Then second, here these are the two images which are available. Now click on copy. Let's go inside and let's control V. So here I will go on to paste. So these are the windows where we can visualize the video file. So let's click on this. Similarly, the second image which we have, so that will also be visible. So simply go inside. So go here, DP0, fluent, fluent, then cell temperature animation. Just click on copy, images file, click on Control V, or let's say Control. So just visualize. So these are the how the temperature curves, temperature animation will be visible. Cell temperature animation. So this represents the scale residual. So for the flow time of 1200 second, we have run the simulation. So you can see the cell temperature animation images. Second, you will see the total temperature system animation, where it shows the temperature of the system, how it is varying, and the total flow time we have taken is 1200 seconds. So this is your cell temperature curve. So the curve is likely to become flat after around 1200 seconds. And the last one is the total temperature of system. So this is again the curve which we are getting. So total temperature system will be slightly on the lower side as compared to the cell.